fine, but you know, I don't have the, what do you call it? Do I have the presentation on the slide? Did you copy the slide?
Yeah, you have the
I don't
slide here?
just, yeah, I don't think I can say it. Yeah, go ahead.
So, put it on here.
All right, so basically, if you look at a company called Monte.com, hello, I say hello, you say goodbye. Hello,
Maybe it's your, this little one, here we go.
hello. Okay, this one talks. Okay,
Check
you
your-
hear me back there?
This and
Not that I'm not shy and quiet. Okay, basically, so I ran across this company, Numenta. You can look it up. Yeah, no, not that one. The other one. Anyway, so go to numenta.org and you see a cover of what they do. And there's other approaches out there, but this one seems to be the most successful. Numenta was founded by a guy named Jeff Hawkins. He made his money on Palm Pilot and Handspring, but his first love was brains, but couldn't make enough money on that then. But anyway, so if you remember the Palm Pilot and Handspring, it had an OCR recognition engine kind of modeled on this idea. But basically, what you do is you take a bunch of input patterns and then you look for, what you do is you classify them into basically a bunch of buckets, and the buckets become attributes. And this becomes the way that you basically identify things like the human brain. So if you're identifying, so let's say you have 100 attributes that define a dog, but you only need like 20 of them to classify it as a dog, and that kind of works for a broad range of stuff. So like, let's say you see an animal and it only has 3 legs, so it's still a dog because, you know, it meets the other attributes. And what differentiates a cat is basically in this field of attributes, you know, you kind of come up with a decision. Anyways, so he wrote this, he and his team wrote this thing called NUPIC, Numenta's Platform for Intelligent Computing. And basically what you do is you can go to that website, there's a whole bunch of YouTube videos, you can go out there and look at it. And basically, they tried to reverse engineer the neocortex, and the way they did that is basically they had an input field, and then basically by associations, it's called Hebbian learning. So you learn that, you know, in the human brain what happens, neurons basically grow dendrites to basically form connections, and so that's how you learn stuff. And you can basically simulate this in the, in software, hardware. And so what you do is, when you see patterns, and those patterns have successfully identified things, then that's called Hebbian learning. So you basically tweak the weights on the associations between input streams, and that becomes how you classify, that's how you make a classification of something. And what they've done, like with the old model, is you look at, they've automated the model building process. So, you know, you can basically expose it to a whole bunch of input fields, and then over time it'll adapt and identify patterns in data, and it'll basically self-learn. So it's like, what's it called? Evolutionary computing. So you basically throw 1,000 models out there, and the ones that are successful you promote, and the ones that aren't successful you demote. And so basically now this is all open source, you can kind of use it. The only license on it is that I guess if you use their stuff for commercial endeavor, you gotta pay them a little bit of money, just because they were looking to fund their next stage of projects. But anyway, so that was called, Numenta, NUPIC, Numenta's Platform for Intelligent Computing. It's basically, and they open source all their software, so they basically have a bunch of C++ code and Python code that basically, Python is mostly the glue code between all the C++ code. And basically, they have a whole bunch of stuff you got there to GitHub/Numenta/NUPIC, I think it's NUPIC legacy. But anyways, and for a while there was, so you can basically download it and try it out. And if you don't have enough resources, they even have something called the Numenta Anomaly Benchmark, which is basically a browser plugin, and in the browser you can basically hook it up to a whole bunch of input signals. And so basically, with that old model, what it does is you get input signals, and it basically you train it to identify patterns in data, and it was structured. The big caveat that they had is that any idea that was added to their source code had to be biologically plausible. And the idea was, well, look, the only model that we have of intelligence is the neocortex, so we should base our development on a model that works, as opposed to, okay, well, here's someone, at that time it was OpenAI, which grew, but you have a whole bunch of associations which were good, but the only model that's really going to be successful in mimicking, those models that are going to be successful are the ones that basically are going to be patterned after the neocortex, because evolution has had millions of years and billions of concurrent tests running over and over before things evolved to be intelligent. So so that was their last project. Now recently, just in the last couple of years, they put out something called Monte, or 1,000 Brain Project. Now the 1,000 Brain Project basically comes from the observation that, the neocortex, it's the upper part of your brain. It's called the new brain. Now the brain is also more than just the neocortex, because there's the old brain. The old brain is the lizard brain. So that's one thing, it's the definition of intelligence. That's what differentiates organisms that don't have a neocortex, is that they cannot assess a situation and go and roll it into the future. And for example, the idea is that, like lizards, they'll follow you, but you hide under a rock, you will fool a lizard, okay? Now, it might be able to find you because it smells you in other ways, or just keeps scurrying around, but nevertheless, it's unable to assess a situation because it doesn't have that neocortex, and that's why primates and, anything that has, a neocortex. Basically, the neocortex, if you look at it, the human neocortex is, if you were to take it out, unfold it, it's the size of a dinner napkin. So it's about 1 millimeter thick and about 6 feet wide, or a meter wide. And so it's all scrunched up on top of that, and it's basically the connections to all your neurons, and they come in there, and then you basically have about 6 layers of neurons, and then in each of these 6 layers, they basically grow dendritic connections to each other, so that's how you learn patterns. On top of that, you actually have cortical columns there, and basically each cortical column becomes a predictive subsystem, and so it basically generates what you see, what it thinks based on the inputs it's seeing, and then somewhere there's a voting mechanism in the ganglia, or whatever it is. There's a thalamus. There's a voting mechanism, and actually, the neocortex, and probably most animals, most animals probably have multiple brains. So you have a left brain and a right brain, and there's whole things about that. And then on top of that, just because we can simulate the neocortex, there's the lizard brain, and then there's also all these other functionals in there, which actually seem to be just as complicated as organs are in the human body. So that, there's a whole bunch of other stuff out there whose purpose we might not quite understand or something like that. So, by the way, I'm going to say that's why I don't think artificial general intelligence is just around the corner. We just don't have that level of sophistication to model that. So that's that. Hold on a second. What am I doing on time? What time is it? I don't have a clock here.
7:11.
Okay, that's it. So,
Right here.
oh, okay, so I can keep track.
7:45.
Because I thought I had 2 hours for my presentation. Look at this. Anyways, so Monte is their latest. So the 1,000 brain theory basically says that there's 1,000 different models in your brain that basically come up with estimates based on their input signal, and then in the end, there's some voting mechanism that decides what happens. So Monte is their other project. You go out to, I think, GitHub/1,000 Brain Theory, and I don't know what it's called. Well, I know it's called Monte, but anyways, this new project, Monte, is more like a framework for building AI systems. And so, for example, one like really big difference between the way that computer graphics work in identifying images and stuff like that is completely different from the way that we think that the brain identifies stuff just based on observations. Okay, so your eye looks at certain things, and it 20 times a second it jumps on, looks for features, and then composes all of this. And then that comes up with a representation of what's going on in reality and what you think is out there. But basically, the idea is that the way that the neocortex works is different from the way that we are doing stuff. So they want to basically enforce building systems that simulate the way that humans do stuff, or stuff with neocortex, with a neocortex does, just because they think that this is the path to AI, and those other paths are just quite superfluous. Just throwing out random statistics, the neocortex has something like 7 billion neurons, 70 billion neurons. No neuroscientists in the audience that throw vegetables at me. And there's probably about 100,000 cortical columns. And so, and the other thing is that each neuron is connected to, at most, 3% of its neighbors. The big advantage that this has is it's a very robust system. It's very fault tolerant. So the idea is that, well, we should just focus on building systems that, mimic the human brain, like, against the vegetarian jihad for Dune fans, right? You ever read Dune?
Yes.
Thou shalt not build machines in the form of human brains. Yeah, so, this is really an attempt to circumvent the vegetarian jihad, okay?
So you need pentats. So
Well, that too.
I'm ready.
I'm ready. Signed up. So, hold on. Well, okay, so obviously I wasn't following my slides. And actually, these break down parts of the neocortex. Okay, so this is the guy, Jeff Hawkins, who basically founded this company, Monte, based on his money that he made from Palm Pilot and Handspring. And basically he's folding it. And actually he's gotten a grant from, I think, the Gates Foundation for a couple million to basically do stuff, and other people, so obviously he has more clout. So it breaks it down. But anyways, and also feel free to interrupt me, because I've been doing and talking about this for 10 years, so there's stuff that I just assume everyone knows and no one understands, like neocortexes and cortical columns. So go ahead and interrupt me if you don't understand what I'm saying.
Okay, Walter.
Yeah.
Did you have a relationship with the company? Did you
No.
work for them?
No.
Okay, just curious.
I wanted a job with them, they didn't hire me, so.
Okay.
Actually, I'm trying to get another job with them again, but no, I don't. I've never worked for them. I've been a fan. They're a small company, like 12 to 15 people. So, and the other big nice thing is that, they open sourced all of these models. Basically, they decided to open source that. They also open source a lot of their research meetings, and also they have a discussion about papers, everything from like attention is all you need review, which is more hardcore AI as opposed to neuroscience, as opposed to having neuroscientists come in there and talk. So basically, the big advantage that this all has is that you can basically download this. Well, you can even download the previous project and try to run it. They have a bunch of hackathons that they ran, and I participated in a couple of those in New York, one in New York and one in California. So you basically try to build systems. Like they had, actually one of the most interesting things they had, like he was actually a drummer from the Counting Crows, and he had a master's in comp sci, and so he was a guest scientist there at Monte. And what he did is he designed a system to basically take music and classify it into MIDI waveforms, and then you can basically do a semantic analysis between music written by one person, another one, by basically just doing and seeing how much of this music was lifted by that music, or inspired by that music, or correlates with that music. He had that. He also had did this on Bach. And basically Bach was a very mathematical sort of musician. He would talk about patterns and then patterns within patterns. And then, eventually, Bach had to stop, but, now it's all been automated, so you can just take music and play it. And so he wrote this program that would take Bach-inspired music and then learn the patterns, and then the patterns within patterns, and just said, okay, well, here's a piece of music that Bach never wrote, but it's inspired by him. And so in the hackathons, his purpose of the hackathons was that you could go try ideas in a community and try to expand them and try ideas that they weren't interested in. Like, they weren't interested in music per se, but the guy from County Crows was, so he basically did that. And they even had a demo of trying to learn patterns, like trying to fly a little helicopter through a forest canopy, where it becomes a very difficult thing, because you have trees and limbs and you want to do that. Go ahead.
So were they able to, if I listen to a piece of Bach, the patterns in Bach,
Yeah.
he would copy, and would that fool a non-musician?
Probably not it would probably fool a non-musician. It fooled me.
Okay, that's good enough.
But it sounds like it, but I never studied music theory, and I'm sure that someone that did probably would say, that's just a piece of, it's like, the AI thing, someone had a joke about ChatGPT, is that it's good in everything that you're not, meaning that, you have it do something for you, and you give it the seal of approval, but you're not really knowledgeable about that. But if you hand it to someone that is, they might say it's nonsense. Okay, but anyway, so first of all, I guess, and I even have a Discord site. I had all of this stuff. Yeah. So basically, what do I want to say? So basically, go to the Discord site. I wish I had more demos, but I didn't have any demos. But so you can download the platform, run it. Actually, they had one interesting thing that they went on a Monte anomaly benchmark, which is basically running a bunch of motors and hooking up sensors to the motors, and you have basically thousands of motors running concurrently, and you want to be able to proactively swap out motors that weren't working, which were about to fail, and you had basically it would pick up patterns in the data that maybe experts could, but the novice person couldn't. So this is and the other thing about it is that as opposed to ChatGPT, this is all open source, and the other thing that I was listening to someone else talk about, so I'm stealing his line, John Crone, is that one disadvantage to all these, ChatGPT and stuff like that, is that it's flooded out a lot of other interesting work in AI, just because ChatGPT and large language models have gotten the lion's share of money and attention. And there's a lot of other stuff out there that's really interesting. And the other big thing is that, what is AI? Okay, it's like, what is mathematics? I took the GRE exams and I did pathetically, and it's like, why? And I talked to my advisor, why did you do poorly? Well, it's because the mathematics that you studied isn't the mathematics that they tested you on. You went through a different curriculum. You didn't learn differential equations by taking this form and manipulating that one. We focused on stability and existence proofs, and figuring out if this equation has a solution or not. Because in the real world, you're not going to take this differential equation, manipulate it in this form and that form, and it's going to be able to amend to that sort of thing. So you want to kind of look at some other ideas. So basically, AI is an overloaded expression, to use a computer science term. It means whatever, or Lewis Carroll said, whenever I use a word, it means exactly what I want it to mean, nothing more, nothing less. And that's kind of what's happened with AI, is that it is a term, and it means whatever it does for the situation at hand, and afterwards, it morphs too, and even like, for example, the big thing is that when the Turing test was finally passed, the first thing people said is that, well, the Turing test was a stupid test, okay, I've got better tests, okay, that, and not because Turing, he never thought about it to the extent that we did, we have hundreds of thousands of people thinking about intelligence now. Turing was one guy, so, anyway, so Monte is this framework for basically building and designing and trying algorithms in a way that mimics the neocortex. And the other big question, I don't know if you ever read this other book, Marvin Minsky's book, The Society of the Mind. You ever read that? Basically, he has like a total, I think, 7 chapters, and each chapter talks about a different facet of intelligence and things that are considered intelligent. And the big thing is you skip from chapter to chapter. It has nothing to do with the previous chapter. And, so that's probably, there's parts of the neocortex that specialize in this, there's parts of that, and then also they're integrated on top of the old brain, the lizard brain. And, how much of that do we understand? Just because we can pick up patterns doesn't mean we're intelligent. Go on.
So, is this based on transistors, ones and zeros?
Actually, it's based on a 3-level circuit. So the neuron, it's basically at the fundamental level. It's I should have said that eventually. It's the underlying representation is a neuron, and the neuron is in 3 states. It's in a dormant state, a predictive state, and a fired state, and so it cycles 3 ways. So fundamentally, it's all laid out, in a computer software. And actually, there was an incentive to try to get a DARPA grant to try to make this in hardware. But the thing about software is you can rewrite it much quicker than you can reprocess your fab factory to, for the next iteration. But fundamentally it's that. But the way that it represents a 3-state system, ideally, and also it scales down. So like I said, the neocortex in humans has 70 billion neurons. Well, there's brains on organisms a lot. I mean, mice have brains. I think there are only 4 layers in thick, and there's probably other primates that are even don't have as many sophistication. But basically, I think the model scales. So it scales from relatively small things you can put on a laptop to if you have a supercomputer, you can stick that in there. So it seems to be robust and scales across a whole bunch of stuff. And it's all in software, so now you can basically try to, the other big speed up, if we come up with ideas and things that work, you can try to implement them in hardware,
So the reason I asked the question was I was talking to Sesame.com. Sesame.com it was a speech app.
Yeah.
And I wanted to ask it about quantum computers.
Okay.
But it actually spoke to me about something called spiking neural networks.
Right.
And I saw recently that they actually have a chip. They've developed a chip. In fact, there's 3 companies. There's IBM and
Yep.
2 more.
Yeah.
And that
it's
actually
called neuromorphic computing.
Yeah, so those chips, they don't have ones and zeros, but they have a spike.
Yeah.
The top of the spike would be the equivalent to a bit like vinyl. You have a spike and you have
that's the firing. That's the firing of the That's the firing of the neuron.
But the additional is that it fires on a frequency.
Yes.
So you have the ability to have parallel processing.
Right. Yeah.
And so it's able to process huge amounts of information. The reason that we're able to have AI is because we use GPUs, and they're able to process huge amounts of data, right? I think that's the case. But with these spiking neural computer chips,
Mm-hmm.
we might be closer to what you were talking about, as in mimicking the neuron.
Yeah, I don't know much. I mean, I hear that tangentially, but I don't know much about
Because
stuff
it just,
like that.
I know that it just recently came out, I think about a week or two ago.
Okay.
It's been around, I think it's the Modi, I can't remember, I forget the name of the chip.
Yeah,
Yeah.
but
I've
it,
actually
as in small ones.
Yeah, okay, yeah.
So that, I think that only just came
I know
out
there's
recently.
a couple different corporations that manufacture this. Now, I looked into this a few months ago, and from what I read, I'm not impressed. A couple of those academic papers that I read on this, they kind of hand wave some important things. The neuromorphic computing with the spiking, what makes it spike, number one? If you try to model the neuron, the neuron, it doesn't like send an you learned in school it's like an electric bolt. No, it's basically charged particles is what it sends.
Right.
It detected. That's what it's doing. But what makes it spike? Number one, why does it spike? So like I've read an academic paper and they would say they have like a series of spikes. Where do they come from? They're hand waving that away. They just assume there's a generator for these spikes. And then they can do some simple thing. And it's like, okay. I mean, have you heard of the worm they always do experiments on? It's called C. elegans, have you heard of it? I think it has like 17 or 47 or whatever, some small number of neurons, like under 100 neurons. They've never successfully put together a model with that wimpy number of neurons and have it do anything useful. So I'm a little skeptical to talk about the entire neurocortex. They can't do C. elegans. So, and you've been studying this company for 10 years, so I've got a number of obvious, I'm sure, not original critiques of this, and I wish it would work. And I have ideas of how to make it work, and those aren't unique either, that thought before. But so you're talking about the brain being a model for computing, and it's a very old adage. It's like we were able to build airplanes when we decided to not try to model it on the bird, and started to learn about aerodynamics, and then we were able to build an airplane.
Okay.
Something that could, something that can go Mach whatever and hold this many G's. Birds can't do that, but we can.
Right.
So. What did they say about that? That very apt observation.
I guess they're saying that it's a freaking. I'm gonna paraphrase them, and I think basically that evolution found a model for intelligence. Therefore, we should focus on trying to mimic and understand that more so than open AI or stuff like that. And maybe that's just, biased statement, but, they basically said that evolution found a model for intelligence, therefore we should focus on that model first and understand that one. And unfortunately, that's like an open-ended build, not just the 100.
I'm not saying you shouldn't be inspired by it, but I'm just saying, okay, we're trying to model the neuron. I think that seems kind of daft. Because
not just the neuron, but basically model the way that, using Hebbian learning, using the way that, patterns, there's a whole bunch of stuff out there. So you basically have neurons, and then, when they start firing, there's like, what's it called, a 6-layer model. And the input layer, neurons come in, and this is actually an old model, this is like the 50s, is that, so you have like 7 layers, and so you have input signals coming in through your neurons, and then they detect things, and then the signals come in, and then neurons grow dendritic connections between each other between the first and the second layer, and then in the second and third, other connections are made, and then this is how we think that, like for example, when you see letters A, it's made up of a whole bunch of segments, and so there's structures there's special cells that identify, slants and vertical lines, horizontal lines, and stuff like that. And so you have a built-in mechanism in your eye cells that are specialized to identify stuff. And so
we get a pre-trained model, but then there needs to be reinforcement for interpretation of what those symbols mean.
Yeah.
That's what I see. One of the things I see missing from neuromorphic computing. How do you reinforce that in a heuristic way? And what would motivate the model to learn something? But one thing it does have that the current deep learning methods don't have, all the deep learning models are synchronous. There, you know, you can do epochs, but it has an idea of a time. We do backprop at the end of each epoch or however you wanna do it. And backprop works great, it brought the neural net forward, but I think in some ways it limits us in some ways as well, what can be done with artificial intelligence. But the asynchronous and very distributed structure of human brains, I think, is useful. But I was just wondering I don't know about this company, but you've been studying it for 10 years, so what do they say about that?
Well, okay.
I'm thinking like something locally analogous to back propagation, but not over the entire neural net.
Well, it's
Might be a solution.
they don't have back. Okay, what's back propagation in neural networks isn't. Well, basically, in this model, it's the growth of dendritic segments between neurons, and so they lead neurons to be coupled. So that becomes the learning mechanism, is that these dendritic connections grow between neurons, and that becomes the identification mechanism. And also it's robust in that these neurons will grow, and then over time they might also retreat.
So biologically, the neurons will actually change their morphology
Yes.
in order to connect to other.
Yes. And they simulate that in their software model. So they're basically simulating the connections that grow. Yeah. By basically they have weights, and then if the weight comes over a certain threshold, then they consider them coupled. Therefore, these signals, when they come together, they give rise to the next level of connections, and so up the hierarchy.
Yeah, because life forms have multiple objectives. So
Yes.
with the models we have like one objective function. For deep learning, there's one objective function. It's going to try to optimize something, but a biological system is trying to optimize many things. Depending, is this one thing that's most important more or less fulfilled? Then I might be interested in optimizing the next thing, and the next thing, and the next thing. Do they have some sort of simulation system that looks at multiple objectives?
No.
I'm disappointed.
Well, but that's not to say, that's not to say you can't add that onto their system. And that's one other thing that they talked about, is that they open source their models so that you can go out there and grab it and experiment it, just because there are small, 12, 15 people. And they've had success in certain things, but they just don't have the time, interest, or inclination to perform other things, so you can build on top of it. And so, basically the whole thing is to provide a framework for other people to build on, and, to basically, go on.
I just have one question. So the spike in your network has the spike and the dip, and then it's got that frequency that you mentioned. What is it about that chip that allows you to parallel process? That's something that I never fully understood. Like, you have ones and zeros, and you have that process.
Actually, my first question was is that an analog? It's not an analog chip. It's a digital chip.
Yeah.
It doesn't have any analog capabilities. Okay.
That was
Because
the
when you
one
said
thing I
spiking, so you're basically sampling. It's a sampled set, and then.
The neuron fires or it doesn't.
Okay.
It's not like in deep learning where you're getting a float. You're got an integer.
Yeah.
It's on or it's off.
So the
So then
thing,
it becomes just, how do you make it learn, since you don't have back propagation to say, getting kick all the weights this hard, all the way back to make it change, as opposed to, well, how do you, in what you brought up, Walter, is how do you get the neurons to grow towards each other? in
There's a
something
reward
that-
function, and
Yeah.
basically when it starts accurately making estimates, the neurons basically, in the biology system, the dendrites grow between each other, and then these neurons become coupled. And on top of that, it's also a system in which they're coupled, but just because they're coupled now doesn't mean they're coupled forever. They have a tendency to decay. I don't know how that's done, but the reward function, I guess, well, in human, the
If it's a
dendrites.
foreign language for a while, you're gonna forget it, you know?
Yeah. And so basically, yeah, they have that, so, and the thing about that is that, they compared that to like, it doesn't oversaturate, like, Kalman filters oversaturate so that, for a while they're predicting stuff, but then the weight matrix is so huge, it starts rejecting new inputs so that, the Kalman filter is super saturated. You gotta you start all over again, or you run multiple Kalman systems and they age out.
Parallel processing, and you hear a lot of it as far as GPUs. Basically what it is GPUs are just smaller instruction set, very limited. It only has a couple thousand instructions, mainly mathematical instruction set. What it does is you get your workload that comes in, and then it pans off individual pieces of that workload. They all work at it once, and then they roll it back up as a set.
Yeah, but
That's
it's
how they do
a
training.
multiple. It's a single instruction, multiple data set, right? Is it? It's not multiple instructions, multiple data, is it? And multiple instruction, multiple data basically means that you have a whole bunch of small little GPU, small little systems running.
So here's the big difference you have to look at from a CPU to a GPU, okay? A CPU needs to know everything of, I type the key, it puts this letter up here, I type this, it makes a noise, I move my mouse, it has to know all of those.
CPUs aren't that sophisticated.
No, I know, but I'm saying is it has to know those instruction sets. A GPU has very limited instruction sets. All it does is just mathematical. And it parses off when it goes to do the problem solving, it parses pieces of that to all of them. And so they do the training that way because they dump all this data in, and they pull all of it back in. And when you go to talk to these large language models, it's inferring that information, and it's doing the same thing in reverse, where you're passing it and it's building a workload and passing you back the results set.
And that's why the Mac 3 Studio Ultra, that has an integrated CPU and a GPU, right? And that's why you can run it's like 512 GB, and you can run these huge models on it. Whereas if you were to do that on the new 5090s, you'd need $30,000 worth. Whereas if I had a 10,000 Mac 3 Studio, I can run 512 GPU. It'll be the equivalent of, I don't know, 200 something VRAM.
Yeah,
So-
see, and the key thing is, if you think about it, early on, you bought your PC and it had a GPU in it.
Right.
And the GPU was responsible for those renderings,
Right.
for those mathematical, foreshadowing, for all of the stuff that the CPU didn't have to do.
Right.
So it offloaded all of that extra fluff
Right.
that then it could specialize because it had a smaller instruction set.
Right.
You didn't have to worry about boiling the ocean.
Because you can't run a huge foundation model on anything at home now. You can't. But you could maybe, if you stack two 512 Ultras, you'd have 1 terabyte, and then you could put one of the big ones on there. Yeah.
NVIDIA's got a small unit that'll do stuff like that.
What the
But you
jigs?
can't get them still.
Yeah, they're like I applied for one. They're $4,000, but if you spent the 10, you'd have a 512 Mac 3 Studio. You could run a bloody big model on that.
Oh, yeah. Yeah, but so that's the difference in between a CPU and a GPU, is the
Say again,
GPU
Tim?
is just a CPU and a GPU is just that smaller instruction
Mm,
set. It doesn't have to know everything, it just has to know to run these smaller calculations.
Right.
And to kind of fall back on what you were talking about, over the years of all of the millions of years of learning, all the stupid stuff that people do, people die. Those people, Darwin, they passed out.
Yeah.
So the smarter ones are the ones that have survived. And those are the ones that have learned certain innate characteristics or certain learning that they passed on to future generations.
Well, not even that, some of it's also, the brain is hardwired for certain things that don't seem to be software recognized. For example, like we have a filter in our brain to recognize faces. And so that's why you sometimes see faces in clouds or patterns
Yeah.
on tile. It's not so much that there's a face there that it triggers that filter that
Pattern
picks up.
recognition.
Yeah, pattern recognition filter.
Well,
So,
and,
Interesting.
you know, animation. You know, you've got a whole bunch of still shots and your brain fills in the little pieces that it's missing.
well, and you don't notice movements beyond, once you start doing 1/10 of a second, and actually there's a whole bunch of cognitive studies, there's stuff I was gonna talk about too. And actually, one of the funniest things I think is that, you really have two hemispheres, and, 100 years ago it used to be thought, and it's kind of gotten out of favor, is that you have one hemisphere for creativity and the other one for analytic thinking, and that was the, that was,
Left, right
but
brain.
that, huh?
Left, right.
But all that's gone away, but actually it's been replaced by something similar, is that you have one hemisphere to deal with organization and basically dealing with things in an organized fashion, and then you'll have another part of the brain that's meant for a disorganized fashion in a disorganized way. So, and evolutionary, some primate was out there gathering berries and looking for the best way to climb a tree, and a mountain lion appears out of nowhere, and you gotta react, okay? You don't think, okay? You just do stuff. And so,
And all the stupid monkeys got eaten.
yeah.
Slow monkeys got
That's
it.
slow.
Well, not just, but it's not just slow, I went hiking with these three other guys, and I was kind of,
Were you
out
the
of
slow
shape.
monkey, Walter?
Listen, no, then they were talking about, well, I haven't worked out in 6 months, and I'm thinking, okay, I have to outrun Jesse Owens, I just have to outrun these two clowns. And actually, I almost went off in a different direction, but then I figured, well, stay, a mountain lion appears, I'll be one against the mountain lion over there, it'll be 1 of 3, and I might be able to trip one of these guys too. But anyways, and actually, the other discussion is about, is AGI around the corner, you're not giving credence to the complexity mechanism that exists there. Like, I said, there's the neocortex, there's the lizard brain, there's the thalamus, hypothalamus, and all these other mechanisms of which I don't think we quite understand their functionality to the whole. And, so that's gonna be, that has to be done, just because, you'll have a system that could put out stupid looking presentations doesn't mean that you have a brain that organized that. If you pull, 1 or 2 people's work, it's plagiarism, but if you pull 1,000 people's work and just a little bit from everyone else, is that learning or is that plagiarism? Well, obviously, with something like ChatGPT, that's what learning is. You're not really learning, you're basically creating associative patterns in a huge, trillion weight matrix, not a matrix, just nodes, as to how much weight should this token followed by that token be given. And you learn that, and then, 6 months later you relearn it and futz with that, and you have more data, but, already, we're already running outside of data, and, there's people pushing for, consuming more data, so, it'll never saturate the system, and maybe that's enough. It's enough to fool, customer service reps, what's your problem? Well, my password, did you check your keyboard to see if your control key is locked? Yeah, it's fine. 90% of people's customer support comes to that, okay?
Is it plugged in?
Actually, yeah. Take the computer back to the place you bought it from and tell me if there's. Actually, I read like when the mouse came out, some people thought it was like you're supposed to operate with your foot, because the sewing machine, women were used to operating the machines with their hands, but then they had a foot pedal to vary the speed and maybe one other thing, and they thought you were supposed to use the mouse. You type with your hands and you select the icon and push with your foot. And you know, there's people who master that skill, right? I mean, people who don't have arms, you know, you ever see someone, they'll eat with their hands. It's like, how can you flex your toes enough? Well, obviously, if your recourse is, you know, you have to teach yourself to eat with your foot. Okay, we gotta get out of here in 10 minutes, whether we want to. Any questions?
I have no questions.
All right, you're gonna download GitHub from
I have
there?
to go to the website.
Huh?
I know, we're gonna have to like get cloud compute to run that stuff, or?
Well, no, you can run it, I mean, depends on how sophisticated a model you wanna run, too, you know? So,
I'm looking at graph neural nets right now.
okay.
Guess what? I'm disappointed. But-
What, twice in one evening?
Oh, well, no,